Hi, everybody. Welcome back to our discussion on molecular analysis of organic molecules. This discussion today is going to go through the beginnings of nuclear magnetic resonance, or NMR spectroscopy. In the framework or the sort of system of organic molecular analysis, NMR is really going to help us determine what the skeleton of the molecule looks like. It's particularly useful for distinguishing between isomers of similar molecules, and especially in conjunction with information from, say, infrared spec that'll tell us something about functional groups, maybe in terms of information from mass spec that might tell us if we have halogens present, or maybe we have certain other heteroatoms available to us in the structure. Maybe we even have elemental analysis that would tell us, just like we talk about in general chemistry, the constitution of the molecule, its sort of formula. NMR is really going to help us distinguish the structural framework for the molecule. From a technical standpoint, the NMR instruments can be relatively small, although most modern instruments are relatively large, like this. We're talking about having a very large magnet, typically with cooling equipment around it, a computer interface, as we can sort of see down here to the right. And if you can sort of squint your eyes a little bit, you can see this gentleman is holding a little tiny sample. So the amount of sample that goes into these instruments is very, very small. The instruments tend to be large, and oftentimes we'll have entire facilities built around them. So these are just some examples of instruments that you might find out there someplace. This one has been around for a little while. At its time when it was built, it was one of the biggest and best instruments pretty much anywhere. But you can see that it has quite the infrastructure for, in this case, a bore size of only a couple of inches across. So what these two slides indicated to us, and we'll talk about in a few slides, is the strength of the instrument. So this is a 900 megahertz NMR. On the previous slide, we had a 700 megahertz NMR. We're going to see what that means, but that's a measure of the strength of the instrument and essentially its resolving power. NMR in general terms, we can talk about being able to analyze the position of magnetic nuclei. And depending on the particulars of the instrument, you can analyze a whole bunch of different nuclei. So in organic, of course, typically we're talking about looking at hydrogen and carbon. Those are the two that we're going to discuss. But once you get into sort of other sorts of instruments, different uses in inorganic chemistry and other things, you may talk about analyzing a host of other potential atoms in the molecule. We're going to focus in on carbon and hydrogen. And at its core, an NMR instrument, if we were to strip away all of the glitz, is a small sample chamber that is positioned in between a very strong magnet. That magnet essentially orients all of the nuclei in one direction. We'll see that in just a moment. Also then, coupled into that sample chamber would be a radio frequency generator that we'll talk about in a moment, something to detect the signals that we're going to see, and then some sort of computational analysis. So when I talk about aligning things and generating radio frequencies, what do I mean? Well, spinning charged particles. So in this case, we're talking about the nuclei of our atoms that are moving. We could imagine those in just a normal sample sitting in a tube on the benchtop. Those nuclei would be sort of randomly assigned in all sorts of different directions. What the magnetic field does, that's indicated here by this B sub naught, this large magnetic field is going to orient most of those atoms, those charged nuclei, in the same direction. The magnetic field of each individual spinning nucleus would be oriented in the same direction as the overall instrumental magnetic field. That's the lower energy scenario here. I like to think about this in terms of a boat floating down a river. You may have a boat for a moment that could be crossways to the river's current, but Just left to its own devices, that boat will eventually turn and be facing in the same direction that the river's current is facing. That's the lowest energy scenario. Now, what happens with that radio frequency generator is that we can apply a small amount of energy to cause the nuclei to jump from the sort of lower energy in the same direction, where their field is in the same direction of the overall magnetic field. We can push that nucleus or flip that nucleus to point in the opposite direction. This is called spin flipping, and this happens by applying a certain radio frequency pulse. Without getting too detailed into the way these instruments work, it's sufficient for us to say that each nucleus that is in a unique electronic environment, magnetic environment, will require a different amount of energy to flip its spin. And so if we apply a small amount of energy, we can flip some type of nucleus. It may take a larger amount of energy to flip a different kind of nucleus. But by doing that, by scanning across those different radio frequencies, we can sort of detect what types of nuclei are in our molecule. What this diagram is meant to indicate is that as the strength of the applied magnetic field, the strength of the instrument's magnetic field gets larger, the energy required to offset that also becomes larger by an equation that maybe looks familiar from some of the discussions you've had in the past. The practical take-home of this is that a stronger magnetic field requires a stronger radio frequency to elicit the same response as we would get on a weaker magnetic field. So I'll get back to that in a moment and why that's of use to us. But it means in practical terms that a larger magnet provides a higher resolution on our NMR spectroscopy. So just as an example here, if we looked at, say, for instance, a applied magnetic field or the instrumental magnetic field being 4.7 Teslas, maybe that's this intermediate step here, spin flipping might require 200 megahertz of energy. At a stronger magnetic field, we would require more energy to flip that. Either way, we're talking about 1,000,000 times lower than IR spec. This is a very small amount of energy in the radio frequency range. So I want to jump out of the sort of nitty-gritty of the way the instruments are working. So I'm going to skip some of the calculations. You can certainly find calculations that allow you to compare one frequency to the other. It's a simple equation that you can look at. But from a practical standpoint, what we're going to be looking at here are magnetic nuclei. So those with odd numbers of protons or neutrons here. So we're going to be looking at, in our case, focusing in on hydrogen 1 and on carbon 13. So we'll see so-called proton NMR and C13 NMR. And as I mentioned before, there are other types of those things. But when we jump forward here, what we can see is that we have this idea that the local environment of any given nucleus affects the magnetic field at that position. So this gets to the concept of shielding. The more electron density that's around a particular nucleus, the more shielded that thing is, and the lower amount of energy it will take to flip it. So we'll see some language here. This is a picture of a typical NMR chart with the x-axis here going from 0 to 10. This is a proton NMR. We'll see a similar sort of language being used for carbon NMR, except that the x-axis goes from 0 up to about 200 or 250 or something like that. We'll see some language here, high field and the word upfield being on the low end of this scale. This is where we have more shielded nuclei, so having more electron density around them. Atoms that are closer to electronegative atoms, for instance, have some of that electron density pulled away or so-called de-shielded from them. And we'll see those showing up here towards the left side. The left side of this area is called the low field or downfield side. And this is where the atoms are somewhat de-shielded. Just to see an example of a molecule, so here's a molecule with some carbons and some hydrogens. And what we're seeing here are the carbon NMR spectrum on the bottom and the proton NMR spectrum on the top. The two different types of protons that are listed here in green and in pink are indicated as these two peaks. What we'll find out in a couple of slides when we look at our reference tables for NMR absorptions is that a plain old alkane, sort of a CH3 group, would show up pretty low on this scale. The hydrogens would show up below 1 on this scale. We're seeing this being pulled up a little bit for the green ones because these hydrogens are kind of close to some electronegative atoms here. Not directly attached to either of those oxygens, but kind of close. And so instead of showing up at a very low range, we see them pulled up the spectrum just a little bit. The pink hydrogens are even more de-shielded, even pulled further up, because their carbon is connected directly to an electronegative atom. And so we see more of that de-shielding effect. We see that signal being pulled further up. Likewise, if we use a different setting on the instrument and we look now at the carbons, we see the same kind of a pattern, that a typical carbon in an alkane is going to show up at a very low reading down here. We'll see those tables also in a few minutes. But our blue carbon is, again, somewhat close to some electronegative atoms, so it gets pulled up a little bit. We see a peak around 20. The green carbon is connected with a single bond to an electronegative oxygen, and so we see that green carbon being pulled up further, maybe 50, 52, something like that. The pink carbon is in real trouble. It's connected with 3 bonds to oxygen. It has a tremendous amount of de-shielding, and so we see it pulled not just up a little bit like the green one, we see it pulled way up into this region of around 170 or so. And so this is kind of a good example of how we can use this to sort of figure out what the electronic environment is, to be able to tell how our molecule is structured. As a technique, NMR is relatively slow. So just as a mention here, if we're talking about normal NMR happening at normal temperatures, we're not going to be able to detect things like chair flips of a cycloalkane. The pink and the green hydrogens here would look exactly the same because at any given moment they could be in these positions with the pink axial and the green equatorial, or in the chair flipped version where they've switched their electronic environments. We can't tell the difference here. Now, if we really cooled the sample down, maybe we could. We could cool the sample down here, dry ice kind of temperatures, and then we would be able to resolve 2 peaks. They'd still be really, really close together, but we could resolve those. In a practical sense, NMR shows us a unique signal for every kind of unique atom in the structure. And so if we look at a molecule like 2-chloropropene, all right, 2-chloropropene. So we have to think about what does our structure look like. If we were to look at 2-chloropropene, see if I can manage to draw on this thing. So it's going to be pretty terrible. But we would have a CH3, CS, oh, that's tragic. We see a CH and a double bond. I apologize, my pen is not working. That's very unfortunate. Okay, pretend that this little blob here doesn't exist because I'm not seeing an eraser tool in my little setup. Super apologize for that. Oh, here's an eraser. Let's see if we can get rid of that, kind of. So what I'm trying to get at with this terrible drawing is that when we look at these, this molecule, and we say, well, how many types of carbon or how many unique carbons do I see? Well, I would see here on the left a carbon with 3 hydrogens that's attached to another carbon. This methyl group would count as one signal on my carbon NMR. Now, this carbon in the middle is in a distinctly unique position. It's taking part in a double bond, and it's connected to a chlorine methyl group. So that would be a second distinct signal that I would see. And thirdly, I have this other carbon off to the side. Okay. Let me actually switch. Let me draw this out in a proper, there we go. Clear away my drawings up here, which I cannot seem to do. There we go. Erase ink. There we go. All right, this looks better. So I have my CH3 group. I have my chlorine-bound part of my alkene, and I have the other part of the alkene. 1, 2, 3 distinct kinds of carbons. I would see 3 different peaks in my carbon NMR spectrum. In the proton NMR spectrum, this depends a little bit on how strong my instrument is from a practical standpoint. Okay, theoretically, what I've got here are, if I were to elucidate my 2 hydrogens, 1, 2, my CH2 group looks like this, okay, 2 hydrogens. Technically what I have here are 2 different environments. I have this hydrogen that's kind of close to the CH3 group, and I have this other hydrogen that's kind of close to the Cl group. They're in slightly different environments, locked into place by this double bond. So on paper, if I were to, analyze this molecule, I would say I have 1, 2, 3 different types of protons. I would expect to see 3 different signals. Now that said, these 2 protons on the CH2 group are pretty similar to each other. So depending on the strength of my instrument, those 2 peaks might overlap or might be hard to resolve. So when you're looking in the textbook and when you're doing homework problems about NMR, keep in mind when it says something like this, it shows signals for 3 kinds of protons. Explain why. Think about the structure of the molecule. Think about the fact that in this case, the double bond is locking us into a particular orientation that does, in fact, make those 2 hydrogens a little bit different to one another. If that had been a single bond, there's free rotation. The hydrogens on that carbon would not be any different. Now, whether you can resolve those peaks, all of those peaks in their entirety or not, is a different question. The problems in the homework are asking about concept. So what should you expect to see? I want to move forward into looking at actual spectra. So again, I mentioned all of this language before. The numbers are based on this molecule that sometimes is included in the sample as a reference point. Sometimes it's not anymore, but that was tetramethylsilane, TMS. That has been set by the field to have an absorption of 0. So 0 ppm right there. Everything else is relative to that. And the reason that we can use this consistent scale on the bottom, regardless sort of what instrument you're choosing to use, is that we're normalizing the spectrum. So the parts per million that's indicated on that x-axis is the shift in hertz. That is the radio frequency that's required to flip those protons or carbon atoms to get the particular signal, divided by the frequency, or this would be the 700 or the 900 I mentioned. 400 is a common spec frequency. The strength of the instrument in megahertz. So hertz divided by megahertz is 1 in a million. That's parts per million. What this means, remember, is that if we had an instrument that was twice as powerful, it would require twice the radio frequency energy to flip the nuclei, but the ratio would be the same. And so whether I did an NMR on a very low-end instrument or on a much higher-end instrument, I'm going to see the same delta value. And so spec taken on different instruments are comparable to one another. Just the better the instrument is, the higher the resolution will be. I also mentioned earlier that in general terms, we're going to see proton NMR signals in the neighborhood of 1 to 10 on that scale, and carbon NMR signals showing up in the 1 to 220, 250, something like that. Normalization can be seen when we look at a slide like this, showing us a molecule with lots of different pieces to it. And this is the exact same molecule analyzed on a relatively low-end 60 megahertz spectrum. Now notice here we're seeing the raw values at the bottom. Okay, so this isn't the ppm scale. These haven't been normalized. The purpose of this slide is to show you how the signals can overlap on a lower power instrument. So if we look maybe starting at the top with our 220 megahertz spec, we can see one signal over here to the left around 320, 30, something like that on the scale. We see another signal clearly showing up here around 260. We see another one around 200. When we divide all of these numbers on the bottom by 220, we would get a standard looking spectrum where the x-axis would be labeled in parts per million. Our 1 would be right here at 220. Our 2 would be over here at 440. Okay, so we would see these signals. If we use a lower power instrument, the 100 megahertz in the middle line, we can see all of this stuff gets a bit crunched. And so it's a little harder to resolve. If we look at a 60 megahertz, sort of a lowest end instrument, these aren't even typically in use anymore. We see all sorts of stuff being crunched together. So when we resolve it, we could still see this information, but it's a little bit harder to pick out. So the better the instrument is, the sort of easier time you're going to have figuring it out, right? Older instruments, we might talk about having scanned things, having to worry about sort of the very particular shielding of the instrument. One of the ways that we get around that is through a concept called signal averaging. This is common across lots of instruments, but it takes advantage of the fact that noise is random. And so random noise that might happen because of, the environment, the lighting in the room, whatever it is random. So if we scan enough times and we average it out, we'll get all of that noise going to zero. Sometimes it's positive, sometimes it's negative, but it's random. But real signals show up. And so the more times we can read the sample, the better signal we're going to get. So if we scanned only once, we might see this kind of a spectrum. If we scanned a bunch of times and added them together with signal averaging, we would see something like this. The noise has been crushed to the bottom, and we see, in this case, 5 unique signals showing up as peaks. This happens in the instrument, nothing you have to do, but just to let you know that it exists. Likewise, Fourier transform is a mathematical transformation that allows us to essentially scan everything at once and let the computer figure it out. And I'm not going to get into FT and how it works, but suffice to say that lots of instrumentation uses FT. And so you'll see that quite often. It speeds things up quite a lot. Detection limit is quite low for NMR because of both of those technologies. We're talking about microgram level, 100 micrograms typically or less for carbon NMR, a couple of micrograms necessary for proton NMR. So we can get very high precision when we measure these things, very low sample sizes. Now, how do we use it? All right, enough of the technical. How do we use it? Well, when we get a readout from a carbon NMR, we can identify what kinds of what kinds of atoms there are, how the molecule is structured, based on charts kind of like this. So every textbook will have its own chart. We're going to see a more detailed version, but just by way of sort of generalities here, we see typical alkane stuff showing up at very low end, okay? When we start introducing electronegative atoms, so our halogens, our nitrogens, our oxygens, we're going to see those guys showing up at higher and higher and higher levels. Again, the more bonds we have to those kinds of atoms, the higher we're going to get. We'll get into our double and triple bonded molecules, or atoms, in the middle of the range. So for carbons, that's going to be up around 100 to 150 kind of numbers. Aromatic rings, importantly, showing up in this 120 to 150 kind of a range. The only things you're going to see way up at the high levels are going to be those carbonyl compounds. So this is where our carboxylic acids are going to show up. This is where we're going to see our um, esters and ketones and that kind of stuff all showing up at the very high end. And this is all due to shielding, like we talked about before. So if we look at a molecule here, this particular one is a ketone, 2-butanone. We can see the color coding. The carbon labeled as number 4 in black is the most, or the furthest away from all of the other electronegative stuff, furthest away from the ketone in this case. So the black carbon is going to show up at the lowest possible of the 4 carbons. Then we see our blue and our green are similar to one another. We can see those two in here. The blue is going to be a little bit lower because there's nothing else connected to it. The green is actually being pulled up a little bit by being attached to that C4 carbon. But we see the C1 and C3 sort of close together, both being one step away from that ketone. They're shifted up relative to the black one. And then we see C2, the actual ketone carbon, way over to the left. And that's hopefully as we would expect by this point. We're talking about now being directly connected, in this case twice, to an electronegative atom. If we look at another example, so again, here's a molecule. Everything's color-coded for us. We can see some stuff going on. So if we didn't have the structure and we saw this C1 blue peak showing up here, we'd say that's sort of in the neighborhood of a normal alkane, but it's shifted up a bit. So I'd expect it to be close to some electronegative center. In this case, we see it's a ketone. Likewise, I would see the signal from the pink carbon way over here, and I would expect that that is the carbon of the electronegative center. So in this case, the carbon of the ketone group. And then I see this mess of green peaks here in that aromatic ring region. And this is pretty typical now for aromatics. So I would expect an aromatic ring. What I wanted to point out in particular here is that we can use this to determine actually the attachment pattern of that aromatic ring. So when we look at that, we can see, let me pull up my pen again here. We can see, there we go. We can see that there's some symmetry on this ring. And so we see carbon 3 here as that bridgehead carbon is in a unique environment. Likewise, carbon 6 is in a unique environment. And so we do see those two as unique peaks, left and right here of the grouping. But then we only see 2 more peaks. Now, there are 6 carbons in an aromatic ring, right? So we would nominally expect to see 6 carbons, 6 signals in this aromatic region, unless there's symmetry, right? So the fact that we have this 1-4 pattern, where we have the 2 groups connected directly across the ring, the fact that we have that pattern makes carbon 5 and carbon 5' in identical electronic environments. And so we see the peak here labeled C5 and C5'. Those 2 carbons are in fact giving 2 signals, but they're overlapping each other perfectly. Likewise, the shoulder carbons here, 4 and 4', are showing up as 1 signal. Now, if we had a different branching pattern such that the symmetry were not there or were different, that would change the number of peaks that we see in the aromatic region. So pay special attention to that when you're going through problems. The sort of pattern that you see, the number of carbon signals you see in that aromatic region can really help you figure out which isomer, which branching pattern you're dealing with. All right, lastly, we need to talk about different modifications of C13 NMR. So everything we've been talking so far is a decoupled, or sometimes called broadband decoupled spectrum. This is just showing us all the carbons in the molecule. So that's a normal spectrum. But there are also these DEPT versions of this. So without getting into the technical details, we can say that there is a technique called DEPT90 that's going to show us only CH signals. So all the other signals are invisible. It's only showing us the CH signals, so carbons that have 1 hydrogen attached. Likewise, we can run a 135 spectrum, and that will show us CH3 and CH peaks as positive, upward-facing peaks, and CH2 peaks as negative or downward-facing peaks. It does not show us here quaternary carbons. So if we had a carbon that was bonded to 4 other carbons, we wouldn't see, or rather a carbon with no hydrogens, I should say, we wouldn't see that at all. So who cares? Well, if we put those together, here's broadband decoupled. Here's the molecule we're looking at. We see a broadband decoupled at the top. We see the CH peaks in the middle, and then we can differentiate here at the bottom. What this allows us to do is to look at this and say, these are all of my carbons on the top spectrum. I know that this one was a CH, and this one was due to a CH. So I definitely had 2 CH groups in there. If we look at the structure, we can see them. There's one right here, and there's one right here. So we've got 2 CH groups. And then we can look at the, erase that there. Then we can look at the bottom. We say we already know about this CH group. We know about this CH group. Here are these positive peaks. Those must be CH3 groups. So I must have 1, 2, 3 different kinds of methyl groups in my molecule. And in fact, I do. I have 1 here, and then I have 2 similar but different methyl groups there, different owing to that alkene. Then I also see 2 CH2 groups, 1 there, and 1 that's a little hard to see right on the 40 line. Those are going to be indicative of my 2 CH2s right here. So by seeing these 3 spectra together, it just gives us more information. It allows us to more easily figure this out. And so I just want to end our discussion of carbon NMR absorptions by showing you this table again. This is a generic table, but it really does a nice job to go over this idea of shielded versus deshielded and the general positions of these absorptions. Of key importance, maybe, are the fact that your heteroatoms here, halogens, nitrogen, oxygen, those are going to show up sort of in this middle-low region. The aromatic ring region, around 120 plus kind of area, is going to be very important, especially for branching patterns on an aromatic ring. And very high absorptions over here are going to be indicative of aldehydes, carboxylic acids, that kind of stuff. So very high on ketones, carbonyl groups. So keeping those sort of 3 generalities in mind and the overall concept of shielded and deshielded and symmetry, carbon NMR can really help you to identify the skeletal structure of your molecule. And by that way, to help identify between closely related isomers. We'll discuss proton NMR in another video. That will help us to distinguish some more information about structure. But for now, look over the carbon NMR problems, practice makes perfect, and reach out if you need any help. Take care.